After having looked for a significant amount of time at alkanes, now let's move on to the next group or class of organic compounds, which we call alkenes. Alkenes, like alkanes, are hydrocarbons, meaning that they are composed of carbon and hydrogens only, or having a few substituent groups. But they contain one or more carbon-carbon double bonds, meaning that instead of sharing a single pair of electrons, they now share a pair or two pairs of electrons. So let's just compare alkanes and alkenes. When we looked at alkanes, we have to remember that they have the maximum number of hydrogen atoms filling carbon's available bonds. What we saw was that carbon can form four bonds, one of which, for a terminal carbon, needs to be taken up bonding to the second carbon, and the remaining three are taken up by hydrogens. For an internal carbon, we have two carbon bonds being taken up bonding to other carbons, and the remaining two are both taken up by hydrogens. As a result, what we see is we get a general formula that says that if you take the number of carbons, that would be represented by n, that could be any number, and you double it and add 2, that gives you the number of hydrogens in the compound. Alkanes are named by taking the root and determined by the number of carbons in the chain and adding the suffix ane. In contrast to that, we have alkenes, which now have a double bond between two or more of the carbon atoms. Because of that, they have less than the maximum number of hydrogen atoms attached, and we call them then unsaturated. As a result, they now have the general formula that Cn H2n. So if you double the number of carbons, you'll end up with the number of hydrogens attached. When we name alkenes, we still have the root, which is determined by the number of carbon atoms in the chain, but instead, to indicate that there's a double bond somewhere in the chain, we put ene at the end. So when it comes to naming alkenes, here are our basic rules. Naming is in the same format as alkanes, but again, remember that the ending isn't an ane as it was with an alkane. It now is an ene ending. This is to show that the compound is an alkene containing a double bond. So the first thing we need to do, just like before, is to determine the longest continuous chain of carbons, but that longest continuous chain must contain the double bond. If it doesn't contain the double bond, then that cannot be the longest chain in an alkene, because the double bond is the most important feature of the compound. 2, you're going to take the number of carbons in the chain so that the double bond has the lowest designated number. So it doesn't matter what the other substituent groups have as their number, it's most important that the double bond has the lowest number possible. Then 3, you're going to identify the varying branching groups attached to the continuous chain just like you did with the alkane. So let's look at an example here. Don't be thrown off by the fact that this looks a little different than what you've been seeing before. It's exactly the same. So the first thing we need to do is identify the longest continuous carbon chain. If you have more than one option, it's the longest continuous carbon chain, which also contains the double bond. In this case, we only have one option, and it happens to go up like this. We won't pay particular attention to it, but because the carbons are staggered, meaning that one goes up and the other goes down, they're on opposite sides of the double bond, we would call this a trans configuration. If those two things were on the same side, we would call it a cis configuration. But that's really outside the scope of this year. You'll look at that more should you choose to take any organic chemistry at a university level. So, looking at this, we're going to now number it to give the double bond the lowest possible number. If it doesn't matter for the double bond, that's when we would look for the substituent groups. So I can name it from the left, going 1, 2, 3, 4, giving the double bond a starting point of the 2, that's where it starts, or I can start at this end and go 1, 2, 3, 4. Again, the double bond starts on the second carbon, so it doesn't actually matter for this particular one which direction we number. Let's check out whether it matters for our substituent groups. Here we've got a chloro group, and here we have a chloro group. Those, regardless of direction, would be located at the 2 and the 3 carbons. So for this case, it doesn't matter at all where we put the double bond. All right, so now let's go about naming it. So we have 4 carbon chain. The 4, remember, has a root of bute. And now, because it is a bute with a double bond, it's a butene. Unlike alkanes, where there was no option, everything had to have single bonds between it, we have to say here where that double bond starts. And this one happens to start at carbon number 2. So this is a 2-butene. We'll come back and deal with our dashes and commas after. We also have on the front of this that there is chloro. There's 2 chlorine substituents. We know that when we name any of the halogens, their ending changes to an O. So there's chloro attached. And there's 2 of the chloro. So this is a dichloro 2-butene. Well, where are those 2 chlorines attached? One is attached to the 2nd carbon, and one is attached to the 3rd. To finish it off, let's just go through and make sure that we put in our commas and dashes. We know that numbers and letters can't touch. They have to be separated by a dash. So I needed 3 dashes. And numbers can't touch. There was no 23rd carbon. So they are separated by commas. At this point, you're ready to move on to look at section 9.6 out of your self-directed notes booklet.